morning, everybody. We have been talking so much of neutral point, delta E required, writing so many equations, so many expressions. There is every possibility that we get lost into all those expressions and we may start losing the interest in this subject. So the best way to revitalize ourselves is let us revisit and make a summary to our understanding what so far we have understood. If you recall how we started, we understood that if an aircraft is statically stable and it can be trimmed at a positive CL or positive alpha, then I need to ensure dCm by dCl less than 0. And just to make things more elaborate, if I am plotting Cm versus alpha, then this condition is dCm by d alpha is less than 0. And to ensure that I can have a trim at a positive CL or alpha accordingly, I need to have Cm at CL equal to 0, which is Cm naught is greater than 0, and here Cm at alpha equal to 0, which is Cm naught should be greater than 0. Right? This is the understanding. We also understood one thing, that if I have an aircraft then this airplane will contribute towards Cm naught, which is this Cm at CL equal to 0 in this case, or Cm at alpha equal to 0 in this case. This contribution, Cm naught, of the whole airplane will come from Cm naught wing plus Cm naught fuselage plus Cm naught because of tail. Although we haven't explicitly derived any expression for Cm naught fuselage or dCm by dCl or dCm by d alpha for fuselage, which we will be doing in our assignment. Also, we know that Cm alpha of the aircraft will have also component from wing, from fuselage, and from tail. Right? And so far, whatever we discussed was, when you derive this expression, we have not put any engine here. Right? Remember this, right? Now, from this plot or this expression, we try to find out what is neutral point. Neutral point, we call it stick fixed neutral point. How did you do that? We derive an expression dCm by d alpha of the whole airplane, and then we equated that to 0, and then from there we got expression for xNO by C or NO by C, the neutral point stick fixed, and in terms of CL alpha of the wing, CL alpha of the tail, VH, etc. You can check your formulation. What is important here is that we have not incorporated any effect of engine, right? So now what we find is, if I draw a line like this, and if this is my reference, we say N naught. Sometimes I write X N naught or N naught, they are same. When I put N naught bar means N naught, non-dimensionalized with chord, mean aerodynamic chord, right? Once we have calculated N naught, which sometimes I write as X N naught or N naught bar, bar means by now you know that it is non-dimensionalized with mean aerodynamic chord. So with this configuration, if this is N naught bar, which is typically, I said, power off. Why power off? Because all this computation, whatever we have done so far, remember, initially, wing contribution, tail contribution, then fuselage contribution, these expressions, there we have not considered the thrust initially. Now then, second case what we did was, we tried to understand, if this is the airplane, if I put a nose mounted engine, and CG is somewhere here, let's say, then we have realized qualitatively that this thrust, whatever is being developed, will give a destabilizing effect. Why? We also argued if there is a disturbance alpha, then some momentum exchange will be here, the normal force, which will be function of alpha in general. And this about CG will give a nose-up moment. And you know, for a positive alpha, any component which gives nose-up moment, that adds to make the aircraft unstable, or it has a destabilizing effect. So what is the message? If the engine was off, that is power off, if the neutral point is here, fixed neutral point is here, the moment I switch on the engine, what will happen? This aircraft, engine being at the nose, ahead of CG, and it has a destabilizing effect, we have agreed. So the overall stability of the airplane will reduce, right? So the N naught with power on will come forward. So this will be N naught power on, because now the aircraft will be less stable. So when the power was off, N naught was here. That means I can bring the CG up to this point. Here only it will become neutrally stable, and if CG is here, it will become statically unstable. But when the power on, then the limit is reduced, because with this sort of engine configuration at the nose, this will add to destability, or it will destabilize the airplane. So the neutral point will come forward. That means now you cannot take XCG up to this point. The XCG, as soon as it crosses this limit, it will become statically unstable, because now the aircraft is less stable compared to power off. As simple as that. Okay. So these are the two things you need to very understand clearly. And then another point comes to our mind, which I try to discuss. Let us see how realistic are they. Suppose I am cruising. I am cruising. Then which N naught should I consider? N naught power on or N naught power off? That means what limit I should be very careful that CG should not cross N naught power on or N naught power off to ensure that it is stable. For cruising means which condition? Cruising, you know, is thrust equal to drag, lift equal to weight, and it is the thrust is there. So what is the understanding? If the airplane having a nose-mounted engine and it is cruising, that means the power on case, then for me, I should consider this N naught for wherever it is required for estimating different parameters, because I know now it is power on case. Suppose I am gliding. Gliding means no thrust. Then which N naught I should use for further estimation of some other relevant parameters, which we will understand soon. If it is gliding, there is no thrust. That means for me, now this is power off case. So this is for gliding. So these are the two extreme cases. One is cruising with thrust on, and one is gliding when the thrust is not there, right? Typically glider flight. However, you will realize there is another condition of flight when I am coming for landing. When I am coming for landing, the thrust is not fully on, right? Ideally, thrust should be as low as possible, or we say the propeller is doing windmilling, right? It's deriving energy from the atmosphere and rotating and developing some sort of a thrust, very low. So that is called propeller windmilling. So you could understand propeller windmilling will be more stable or less stable compared to power off. Power off is the most stable case. The moment it is windmilling for nose-mounted engine, it will be less than power off. So it will somewhere here, I said N naught propeller windmilling. However, it will not be less than N naught power on, because it's the full thrust is there, or appreciable thrust is there. Here it is only windmilling, right? Okay. So this is the limit for N naught propeller windmilling. And when that has to be used, so now you know if it is landing, then wherever I want to use the stick fixed neutral point, I will be using N naught propeller wind milling. So going back here, this is for gliding, and for that means this is your N naught power off, and then for cruise we have already realized should be N naught. It is better to put N naught bar. It is power on. This part is clear? Okay? Now we see how these things to be used. Okay? That is more important. Second phase we did was delta E equal to delta E naught plus d delta E by dCl trim into CL trim. This was what? We recall that if this is CM and this is CL, if the airplane is trimmed here, now you want to fly the airplane at different CL here, let's CL2. So because statically stable, it will generate negative pitching moment. So I need to nullify that so that this line becomes like this. To neutralize that negative pitching moment, I have to generate positive pitching moment. And for that, I have to put elevator up, right? So how much elevator up is required for this CL trim, we will calculate from here using this. So this I always say is delta required, or you can write delta E trim. What does it mean? If I know delta E naught value, if I know this gradient, for a given CL trim, I know how much elevator I have to deflect. Clear? That we have done it. If I see this clearly, I see this is Cm naught by Cm delta E, and this is minus dCm by dCl divided by Cm delta E into CL trim. I recall again that when we derive this expression, we have made some approximation on relative magnitude of few derivatives, but this is a good enough approximation. This further I can write as minus Cm naught by Cm delta E plus this is dCm by dCl is nothing but xCg bar minus xn naught bar, right? You could see here, instead of n naught bar, I am writing xn naught bar. So they are the same. So this will become x, or let me write n naught bar, you will get confused unnecessarily, minus xCg bar divided by Cm delta E into CL trim. And this is delta E trim or delta E required. Concentrate here. Okay? Now see here. Suppose I am doing a cruise at say CL equal to 0.2, and let's say neutral point. Okay, CL equal. Suppose, let's repeat again. Suppose we want to cruise at CL equal to 0.2 for a given xCg location, right? xCg is fixed, some location, right? Now, when I want to know how much delta trim I should have for CL equal to 0.2 while cruising, this is important. How do I use this formula? This is known for the airplane. Question will be, what N naught should I take? Should I take N naught power on, N naught power off, or N naught propeller wind milling? You know very well now, because it is cruising, so I should take N naught power on. This value will take, right? Because cruising thrust is on. Correct? Now similar, so for delta E trim for cruise, I will use N naught power on. Right. Now let us say, suppose it is coming for landing. That is, what is the case of landing? Propeller windmilling, right? N naught should I use? I should use N naught propeller windmilling. So it will be N naught should be corresponding to propeller windmilling. Okay, suppose we are coming for gliding, right? We want to glide, switch off the engine, and we are not allowing propeller windmilling. Or in a simplified case, suppose I am doing a gliding flight with a glider which doesn't have an engine, let's say. Then, if I want to trim the glider for different CL, which N naught should I take? I know for gliding, I should take N naught bar, there is no engine, so power off. This is the understanding. I hope now you get the clarity. What is the importance of neutral point for power on, power off, propeller windmilling, and how they are going to affect delta E trim. Please understand, a different value of N naught means you are having a different static margin, different degree of stability for a given CG location. As N naught changes for different cases, so static margin or stability margin will change, so accordingly delta E also will change. Nothing new we are doing. So this should be kept in your mind while solving a problem, and we should not lose the insight what we are doing. Okay. One thing we should also understand and keep on telling ourselves, when we are talking about N naught, what is the definition of neutral point? It is a point on the aircraft. If I put the CG at that point, aircraft will become neutrally stable, or if I put the CG beyond that, the aircraft will become statically unstable, right? That is the definition of N naught, okay? But now see one more thing. In a way, N naught is telling us what is the most aft CG permitted. Am I correct? Isn't it? Because you know, if the CG goes beyond N naught, it will become statically unstable. So it is telling, oh man, the CG cannot go beyond this point, beyond this neutral point. Now think of, you have N naught power on, N naught gliding or power off, and this is windmilling. From designer point of view, what should you put restriction as the most aft restriction for the center of gravity of the airplane? Up to this? If CG can be taken up to this? Definitely not, because if you tell like that, then during power on case, it will become statically unstable, right? So your most aft CG permitted will be governed by N naught power on. So this should be very, very clear that N naught power on, okay, will decide most aft CG location for nose mounted propeller engine aircraft. This should be very, very clear. I repeat here again, you know that N naught means if the CG is beyond N naught, the aircraft becomes statically unstable. So now you have got N naught power on, N naught power off, N naught propeller windmilling. So as far as design is concerned, you should ensure that, because power on means you're cruising, and that is the lowest, that means my CG should lie somewhere in this domain. Should not lie here, 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 or here. This is one learning, right? And of course, we are talking about an aircraft which has a nose-mounted engine. You could understand that if the engine is put behind the CG, the discussion will become different. But mostly engines are in the nose mount or ahead of CG. So we are focusing on this, right? This is one. So most aft CG, we know how to draw in a specification. It should not cross beyond that. Because N naught power on, you will compute based on the wing characteristics, tail characteristics, fuselage characteristics, and the engine thrust characteristics, that is how the engine thrust is changing with alpha, etc., etc. It has nothing to do with CG, right? So this is done, most aft. The question comes, how do I decide most forward? And who will decide? What is the philosophy of most forward? If the CG is ahead of neutral point, it is going to be stable. From stability point of view, there is absolutely no issues. As CG goes, take the CG forward, 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 and forward, it will become more and more stable, statically stable. But is there any restriction? Please understand, before we do some formulation, we can conceptualize that if an airplane becomes highly stable, then it is very difficult to change or trim the airplane at a particular CL, because I may not have that much of elevator control power. We have seen that. So now, based on that philosophy, we'll see what is how best we should understand how do I locate, how do I specify the most forward CG location, right? Before discussing on most forward, let me take a simple example, right? Let's say delta E equal to delta E naught plus d delta E by dCl is nothing but minus, so it is be n naught minus xCg by Cm delta E into CL trim. Right. Let us take some values. Let's say I take Cm naught. These numbers are taken just to give some illustration of a concept. Okay. So allow me to take these values. Cm delta E is minus 1.0 per radian. Please note down that this is per radian. Okay. And let's assume n naught bar is 0.5. With these three numbers, I can easily find out what is delta E naught. What is delta E naught? It is minus Cm naught by Cm delta E. So this is minus 0.04 by minus 1.0. So this is 0.04. So that is the value of delta E naught, correct? And if I now simplify, what do I get? So I get delta E equal to 0.04, then plus n naught is 0.5 minus xCg bar divided by minus 1. So Cm delta is minus 1. So I put it here a minus sign into CL trim. Right. Now see this case. Think of landing. So when I put n naught equal to 0.5, because I am studying a case landing, that means I am clear that this is propeller windmilling case. Okay, let's say it is 0.5. Now let us do a tabulation. I want to see what is the effect of moving CG forward for delta E required for a particular CL trim. Okay. Let me assume CL trim is equal to, let's say, 0.6. Okay? So then what is this expression will become? You can yourself do this, 0.04 minus 0.5 minus xCg into 0.6. Okay, the CL trim value is 0.6. Let us take a case delta E for different xCg. Okay, so let's say xCg as 0.4. If xCg bar is 0.4, what is the delta E required? So now you know that delta E required is 0.04 minus 0.5 minus xCg into 0.6. Right? So if xCg is 0.4, so this value becomes 0.1. So 0.1 into 0.6 become 0.06. So 0.04 minus 0.06 will be equal to minus 0.02. Let us check again. XCG is 0.4. So 0.5 minus 0.4 is 0.1. 0.1 into 0.6 is 0.06. This is minus 0.06. This is plus 0.04. So delta E required is minus 0.02. What is the unit here? This will be 0.02 radian. Why radian? Because Cm delta E we have taken per radian. And you could see that this Cm delta E, if it is in per degree, then it would have been in degree. But because Cm delta E is per radian, this delta E also will come per radian. Please be very, very clear about this. Okay. So to get a feel, roughly I can write this equal to 0.02 into 57.3 degree. So how much it is? So we are seeing that for CL trim equal to 0.6, for an XG location of 0.4. So let's say, let me draw this. This is a reference. Let's say this is the XCG 0.4, and this is the N naught. We know this is power propeller windmilling, because it is propeller windmilling case because we are thinking in terms of landing. Am I correct? Yes. Right? Okay. Why we are talking about landing? Because we are trying to find out most forward CG. How far this CG can go forward. We have seen for one tentative case, if I take XCG equal to 0.4, then delta E required is minus 0.02, which is roughly minus 1. My calculator shows 1.146 degree. Okay, right? Am I correct? Yes. Now think of a second case. See, if I take the CG at 0.2, if it is 0.2, then what will happen here is delta E at XCG 0.2 will be 0.04 minus 0.5 minus 0.2, this is 0.2, is 0.3 into 0.16 is 0.18. This is correct? Now XCG is 0.2, so this value is 0.3. 0.3 into 0.6 is 0.18. So I get the value as 0.18 minus 0.18 minus 0.04 is how much? 0.18 minus, so this will be minus 0.14 radian. Correct? So what is 0.14 radian? 0.14 radian, let me check. 0.14 into 57.3, and that will be 8.022 degrees. So this is 0.14 radian, and that is, if I put this CG is here, 0.2, and that is equal to 8.02 degree. So you are seeing that as I am taking CG forward, the elevator angle required to trim is increasing. Now if I take XCG at 0.1, let's say 0.1, what will happen? Again, if I calculate by this expression, then XCG is 0.1, so this difference is 0.4, 0.4 into 0.6, 0.24, minus 0.24 plus 0.04, so delta E required will be 0.04 minus 0.24, so this is equal to minus 0.20. So what is 0.20 radians? That means, let me again calculate, that is 0.2 into 57.3 equals to 11.46. So this is 0.20 radian and equivalent to 11.46 degree. So do you see this? How this is happening? That means if I take it further, this delta E will further increase one way. But you have a delta E limit. So delta E max will have. Right? Suppose delta E max was 10 degree. Suppose delta E max was 10 degree, plus minus. Generally it is plus minus 15 or plus minus 25. Suppose delta E max is 10 degree, then this result shows that I will not be able to trim the aircraft at CL.6 for a configuration which is having CG 0.1. This is not, I am not able to trim this airplane for this CG location, because to trim this airplane at 0.1 location, I need 11.46, but my delta E max is, let's say, 10 degrees. If this delta E max is 15 degrees, I should be able to do it. Okay? Remember, this is for CL equal to 0.6. But when you are landing, then CL is around 1 or 1.2. So now let's see what happens if it is 1 or 1.2. You could easily see that if this is 1.2, then the delta requirement will further become very, very stringent, and you will have to be very, very careful that how far I keep my CG of the airplane will be decided by the delta E max limit. Okay? Let's do one example. Suppose we are doing it for CL is equal to, let's say, 1.0 during landing, and I am now trying to calculate delta E. Let me write this here, CL equal to 1.0. Or let me erase a few things so that you don't get lost. Let's say now I am doing for CL equal to 1.0. Typically these CLs are for landing and takeoff, right? I am talking about landing. And this is XCG. Now see, for CL 1.0, I have landing like this. If I now want to see what is happening for 0.4, then I go back here, XCG is 0.4, so 0.5 minus 0.4 is 0.1, and this is no more 0.6, this is 1.0, right? CL trim, I write CL trim. So how much it is? For XCG equal to 0.4, this is 0.5 minus 0.4 is 0.1, 0.1 into 1 is 0.1, minus 0.1, so delta E becomes minus 0.06 radian. Am I correct? This is difference is 0.1. 0.1 into 1 is 0.1. So minus 0.1 and plus 0.04 is minus 0.06. So this is minus 0.06 radian. What is this in degree? Let me check. This will be 0.06 into 57.3 equal to 3.5 degree approximately. Notice here, from 1.1 it has become 3.5 degree. And when I say negative, negative means what? Elevator up. Negative means elevator up. Correct? Now if I come to 0.2, how much it becomes? You see, 0.2 means 0.5 minus 0.2 is 0.3. 0.3 into 1, 0.3 minus 0.3. So delta E will become, in this case, will be 0.3 minus 0.3 plus 0.4, so minus 0.26. Correct? You see here, this difference, if XCG is 0.2, this difference is 0.3. So you can see 0.3 into 1, this is the CL trim here. So 0.3, so minus 0.3 plus 0.04 is minus 0.26. Again, this is radian, and 0.26 radian means, again I check, 0.26 into 57.3 equal to 14.8 degrees. So this is minus 0.26 radian, and this is 14.7 degrees roughly. What is the message? Instead of 8 degrees, now it has become 14 degrees because you are now trying to land at CL equal to 1.0. And let's assume that delta E max is less than equal to plus minus 15 degrees. Now let us see for 0.1, then come back here. This will become 0.5 minus 0.1, so 0.4. 0.4 into 1, this becomes 0.4 into 1 is 0.4, the minus 0.4, so this delta E becomes now minus 0.36 radian. So what is minus 0.36 radian? Let us calculate. 0.36 into 57.3 is equal to 20.6 degrees. So this gives me minus 0.36 radian, and that means how much? 20.6 degrees. So around 21 degrees. All are minus, right? Wherever I'm writing, this is minus. Please understand this. It's also minus. This is also minus. This is minus. One minus and I have missed, I'm correcting it here. Now coming back here, you see, for CL equal to 1, that is CL trim equal to 1, typical value for landing, I see that if my CG is at 0.1 C, then the requirement delta E is 21 degree, but limit is 15 degree plus minus elevator. So I will restrict my forward CG by the elevator deflection limitation. So I will not go beyond 0.2. This is my, I'll stop it here. So this will be my most forward CG as far as these examples are concerned. Is it clear? So you could see that for CL equal to 1, my most forward CG of the airplane will be restricted by the CG, most forward CG location 0.2. If it is CG is going ahead of 0.2, it's 0.1 most forward, then this limitation, that delta E max is effective only up to plus minus 15, won't be able to trim it. So my most forward CG will be restricted by the elevator deflection limitation. Clear? For 1. Similarly for 0.6 we have seen this. Typically for landing, this is the number you look towards. Next class you will see during landing there is something else happens that also restricts your elevator availability for trimming, and that has an effect on most forward CG location. So we'll do that. Okay? Thank you.